Okay, so section 4.2 has to do with the unit circle. We've done a little bit of work in the last section just with theta and using radians, and then doing some calculations to find principal angles and reference angles, and we're going to be referring to those as we're using this information with the unit circle. So a unit circle is a circle that has a radius of 1 and the center is at the origin of a Cartesian plane. So on your page you have the example here, your Cartesian plane, of course, with the x and y axis, and the unit circle with whatever, it doesn't matter what the length you're looking at, because it's a unit, it of course is a length of 1. The origin has to be at the center, so this point right here couldn't be at anywhere else. It has to be right at the center of the circle for it to be a unit circle. So if we know that this is a unit circle, whoops, I'm just going to pause and do a little realignment here again. Okay, so if we put a point on that unit circle that is on that terminal arm, we say that this point is at xy. And the reason for that is that if you think of this point being on a Cartesian plane, the length of it going this way would be x, and then the length of it going this way would be y, or y distance from the origin. So this is our angle, what we call theta. This is side x. Then if we were to drop down a perpendicular line going from our point on the circle to the initial arm, we would make a right triangle here. So on this right triangle, then we know that this is side x. This side here would be side y. It corresponds with that. This was our radius. And we know that our radius has, because it's on the unit circle, would be 1. So r is equal to 1. So when we're looking at our points here, to write an expression for sine theta, sine, of course, if you've forgotten, our acronym is SOHCAHTOA. So sine is opposite over hypotenuse. So sine of theta is our opposite over hypotenuse. So in this case, opposite of theta would be side y. And the hypotenuse is our length there of 1. So sine theta is actually equal to y. The expression for cos theta then, cos of theta is equal to adjacent over hypotenuse. So adjacent to theta would be x. Remember, adjacent is the side that is beside it, the angle, but not the hypotenuse. And our hypotenuse, of course, is, so in other words, cos theta is equal to x. So that's when we're talking about a unit circle. Tangent then is equal to the opposite over adjacent. So opposite of theta is side y. Adjacent to theta is side x. So if sine of theta on a unit circle is equal to y, cos of theta is equal to x, then we can use that information, this from here, and substitute it into our points here. So our point would have the same values. Our xy points would be the same thing as finding cos of theta, would be the equivalent of the x coordinate, and sine of theta would be the equivalent of the y coordinate. And that's just from simple substitution from using our two trig functions on a unit circle. So now we're going to look at what or how the Pythagorean theorem connects to the equation of the unit circle. So the equation of a unit circle, the equation, first of all, just of any circle, is x squared plus y squared is equal to, would be r squared. So in this case, for a unit circle, we would have x squared plus y squared is equal to 1, or 1 squared. If we weren't talking about a unit circle, then it would just be called the equation of a circle. And all it would be is your radius squared. So if I had a circle and it said that my radius was 4, then I would have x squared plus y squared would equal 4 squared, so it would equal 16. And I kind of jumped ahead here and did both of them at the same time. So if a unit circle, if it says unit in there, then we know right away that our r is a 1. So that would be our formula. If we are looking at a circle with a radius of r where they haven't given that to us, then that's our x squared plus y squared equals r squared. So knowing this formula and keeping in mind what it looks like, what our unit circle on a Cartesian plane would look like, we can do some calculating. So it says, which of these points are on the unit circle? So because it told us this is a unit circle, we know that our r is equal to 1. So that means when we substitute, we don't even have to write an r there. We can just say that that's equal to 1. So x squared plus y squared is equal to 1. So in order for this point to be on the unit circle, when I square and add those values, I have to have it equal to 1. So it's like doing a check for a solution. So I take my 1 over square root 2 and I'm squaring it, plus my square root 3 over 2 and square that. And I want to know if it equals 1. So you put the little question mark above it so that you know that this is like a check. And then you try. So 1 over square root 2 squared, so 1 squared is 1, square root 2 squared is 2. Square root of 3 squared, all squared, is going to be 3. Square root of 2 is 4. So I'm still checking, does this equal 1? So 1/2 plus 3/4. If I change this into a equivalent fraction, I have 2/4 plus 3/4. Checking if it equals 1. Well, obviously it's 5 over 4, not equal to 1. So this is not on the unit circle. So 1 square root 2 over, and square root 3 over 2 is not on the unit circle. So that's the steps that you use if you're trying to find out if a point is on a unit circle. Okay, example 2. 1/2 and the other point is square root 3 over 2. So I do the same thing. I'm just going to move this down. So I take my x squared plus y squared is equal to r squared. So 1/2 squared plus square root 3 over 2 squared equals 1. That's what we're trying to find out. So I have 1/4 plus 3/4. And we'll see if that equals 1. Well, 4 over 4 equals 1. So that point is on the unit circle. Okay, next example says, determine the coordinates for the points on the unit circle which satisfy all the given conditions. Draw a diagram in each case. So they've given us some of the information for this. We have to find out the rest. We know this is on a unit circle, so that means that r is equal to 1. The x-coordinate is given to us. They want us to find the other coordinate, so we need to find y. So whenever you're doing these, it's always a good idea to list out your variables to see what you have and what you need to find. So my r, because they've told us it's a unit circle, is 1. My x is equal to 1/2, and my y value is what I'm trying to find out. So I need to draw a diagram. So there's my diagram. This is going, it's supposed to be at the origin, and then I'm dropping this down here. So this is what it looked like. This I know is 1/2 because that's my x value. I don't know my y. And my r is equal to 1. Okay, so now when I substitute, I have x squared plus y squared is equal to r squared. So my x was equal to 1/2 squared plus y squared is equal to 1 squared, which is just 1. So I have 1/4 plus y squared is equal to 1. Get y by itself, so I have to subtract. So y is equal to, y squared is equal to 3/4. I don't know why it's doing that to me. Okay, so if y squared is equal to 3/4, then I square root both sides. So y is equal to plus or minus square root 3 over 2. So all I've done there, and remember from past units, I can't remember which unit that was, maybe in unit 1 or unit 2, when you square root, you have to take the positive and the negative, and we did this in pre-calc 20. So square root 3, we just leave as a square root of square root 3, square root of 4 is equal to 2. So possible cases where this is, in this case here, let me do this in purple. So this one here, we're having y is equal to 1/2, then this y would equal the positive square root 3 over 2. For y to be a negative square root 3 over 2, because I have to do it for both cases, then my x value still has to be a positive 1/2. So I know my x is going to stay in the same spot, but now in this case my y is going to be the one that's going to be in this quadrant here. So this one has y equal to negative square root 3 over 2. So there's two possible solutions to this graph. Okay, example B says that the y-coordinate is equal to negative 1 over square root 2. And the point is in quadrant 3. So because they've given us a little bit of a restriction on here, we might not have two solutions when we're done. So first of all, we list, okay, I don't know what my x is equal to. I know my y is equal to negative 1 over square root 2. And my r, of course, the unit circle, so it's equal to 1. So if I do my solving, x squared plus y squared is equal to r squared. Don't know what x squared is. R squared is equal to negative 1 over square root 2 all squared. And that is equal to 1. So I have x squared plus 1/2 is equal to 1. So the square of negative 1 over square root 2 is just 1/2. So I have x squared is equal to 1 minus 1/2. X squared is equal to, 1/2. I lost my train of thought. Square root. So x is equal to square root 1 of the root. And you could rewrite this as plus or minus 1 over square root 2. And for right now, it's okay to leave that square root in the denominator. So now I have to see, okay, where is this going to work? So there's my Cartesian plane with my lovely circle. So I know my y is equal to negative 1 over square root 2. So that means that my y could be in this quadrant, or it could be in this quadrant. If I were to finish off my diagram here, this would be negative 1 over square root 2, and this would be negative 1 over square root 2 on the y, even though it's not even. Okay, but this one said that my graph had to be in quadrant 3, so that pretty much takes care of that one. I didn't even have to draw that one because of that quadrant 3. So then that means that my x value for this solution has to be on this graph, and my x on here would be a negative 1 over square root 2. So my solution to this one would be negative 1 over square root 2 and negative 1 over square root 2. So because this one had that restriction on there of the quadrant 3, we can't include that quadrant 4 diagram. Okay, so special triangles. You might remember from, we use special triangles in workplace math in grade 10, and then we use them in our pre-calc last year, and I think we may have used them in foundations. I can't really remember. And then we're going to be using them when we're dealing with trig functions in the unit circle on here. So in this example here, this of course is a 45, 45, 90 triangle. So this is 45 degrees, this is 45 degrees, and that's our 90 degrees. And if you remember when we talked about it before, we did this as values of 1, 1, which meant that the hypotenuse was square root of 1 plus 1, which is square root 2. When we're dealing with a unit circle, because we want our radius, or our hypotenuse, always equal to be 1, that means we have to divide this, or our special triangle, by whatever's in the hypotenuse, so that it'll be a value of 1. So if it's a square root 2, that means I have to divide it by square root 2 to get 1, which means I have to divide every other side by square root 2. So this is putting it in unit measurement. Okay, so 30, 60, 90 triangle, which is what this one, or this one to start with when it's all together, would be an equilateral triangle with your angles being equivalent at 60 degrees. So this whole amount here would be 60 degrees. And if we are looking at, actually, well, I could write those in, I guess it doesn't matter. We're going to use values of 2, and I'll explain why we use values of 2 here. So in the 30, 60, 90 triangle, we said that the side, and remember it went with the smaller angle had to have the smaller value. So our 30 degree, and this is cut in half, that's why it's 30. This side would be 30 as well. The side opposite the 30 has the smallest value, which is 1. The side opposite the 60 degrees has a value of square root 3, and then the side opposite of our hypotenuse, which is the longest side, had to have the longest value. And when we could actually do a calculation for this, and that's why I put the 2's on here. To find out these 1 and these square root 3's, what we've done is we've said, okay, we've got a base triangle with sides of 2. When you drop down when you drop down a right angle from one of those corners, it cuts this perfectly in half. So it took our 2 and divided it into 2 parts, so this was a 1. And then we would have used Pythagorean theorem with A equals 1, B we're trying to find out, so B is this side, and c is our hypotenuse, which had a value of 2. So when we do 2 squared minus 1 squared and then square root it, we get square root of 3. But again, because we're dealing with the unit measurement, we have to take whatever the hypotenuse is, that value, and divide it so that it equals 1. So since this is a 2, we're going to divide it by 2, so this equals 1. So that means we divide each of our other sides. So for a unit special triangle, our radius or our hypotenuse, I keep interchanging those words, and you'll see as we do questions why. Our hypotenuse has to have a value of 1. So that means that we had to divide all of our other sides so that they were equivalent to what we did to the hypotenuse. If we're thinking of this in radians instead of in degrees, 45 degrees, so if I use my formula from last time, I'd multiply this by pi over 180. So 45 goes into 180 4 times, so this would be pi over 4. So 45 degrees is the equivalent of pi over 4. 30 degrees, so 30 goes into 186 times, so this is the equivalent of pi over 6. 60 degrees, so 60 times pi over 180 goes into there 3 times, so this is the equivalent of pi over 3. Okay. I thought there was another question. So the next example says, what are all the coordinates of the given angles on the unit circle? So if our theta in this case is equal to pi over 3, so pi over 3, and then these ones, you can turn them into degrees if it helps you, but you should always use your whatever is the units that they use that in your final answer. So pi over 3 is the same as 60 degrees. So I know because it has a value of pi over 3 or a value of 60, that is going to be the equivalent of this one here. So I'm going to use the 30, 60, 90 values in order to solve this. So if this is a 30, 60, 90 triangle, what I do then is I draw my unit circle on my Cartesian plane. So if this is, and I'm just going to do a sketch here, this is pi over 3, so this is my theta. That's equal to pi over 3. They want to know what are my x and y coordinates. Oops. So on a 30, 60, 90 triangle, sorry, I need to put that the other way. That should be 60 down there. That's what I'm drawing there. So if this is 60 degrees, then this is my 30 degrees. So I know the side opposite my 90 is 1, so this value here is 1. The side opposite the 60 degrees is the square root 3 over 2. And the side opposite the 30 degrees is 1/2. So if I take a look at this on the Cartesian coordinate plane, this value here is 1/2. This value here is square root 3 over 2, which translates to x being 1/2 and my y being square root 3 over 2. So the coordinates for this then would be 1/2 and square root 3 over 2. So when you're doing these, you have to plot them on your Cartesian coordinate plane so you have them in the right coordinates, or in the right quadrants, and then take a look at, okay, which of my special triangles can I convert this to be? So this is where reference angles are going to come into play. And you'll see this in the next one. So 7 pi over 6. If I convert this into degrees, whoops, 180 over pi, 6 goes into there 30 times, pi and pi will cancel, 7 times 3, so that's 210 degrees. You could leave it in as 7 pi over 6, and if you remember from our discussions before, when you draw on your unit circle here, remember this is 0 and 2 pi, this is pi over 2, or half, and this is a full pi, and then this was 3 pi over 2 in this area. So pi would be the equivalent with a denominator of 6. This would be 6 pi over 6. So that means I have to go another pi past that to get my 7 pi over 6. So I'm just going to do this in another color. So this is going to be like that. It's going to be a fairly skinny triangle. So this is what this would look like on here. So 210 degrees, or if you think of it in the radians, 7 pi over 6 is close. It's in quadrant 3. So to find my reference angle, I take my theta and I subtract my value of pi, or in this case it's 6 pi over 6. So my reference angle is going to equal 7 pi over 6 minus 6 pi over 6. So my reference angle is pi over 6. If you left this in degrees, I would have my reference angle is equal to measurement of my angle, which was 210 degrees, minus my 180, which gives us degrees. So either way, you could do it as a pi over 6 or as a 30. And on our special triangles here, you see pi over 6 corresponds with 30. So again, then, that means I know I'm going to use the 30, 60, 90 triangle. Oops, went too high there. So if I'm using the 30, 60, 90 triangle, then that means that this is my 30 degrees here. The side opposite the 30 degrees has that value of, and I'm just looking off of here, off of 1/2. I know my hypotenuse is a 1. And then the side opposite that, which would be opposite the 60 degrees, is that square root 3 over 2. But now what you have to do is you have to take a look, okay, which quadrant is this in? It's in quadrant 3. In quadrant 3, my x is negative, and my y is also negative. So my answer to this one, the coordinates would be at negative square root 3 over 2. And my y was at negative 1/2. So there's a few parts to it. You can do the conversion from radians into degrees, or you could just leave it in radians. You have to draw it on your unit circle, find your reference angle, and then your reference angle will tell you which triangle you're using and which angle in that special triangle you're going to evaluate from. And then you have to say, okay, which quadrant is it in? Are my x's and y's positive or negative? Okay, 3 pi over 2. So if theta is equal to 3 pi over 2, if I draw my unit circle, well, 3 pi over 2 is right there. So it's going straight to this line here. So this point here would be 0, 0. This point here is at 0, 1. And sorry, that's not 0, 0, that's 1, 0. this point here is at -1 and 0, and then this point here is at 0 and -1. So this is right on, because it's right on an exact value of 3 pi over 2. Then I know my coordinate for that point is going to be at 0 and -1. If the question said theta is equal to pi, then that pi value would be right here, so then that would be here. So my answer would be -1, 0 for the coordinates. Okay, the next example says, what is the angle formed when theta is in between 0 and 2 pi by the following points? Okay. So I know that this is my x value, and I know this is my y value. So for x to be a -1/2, I know it's going to be on this side here, and y is positive, so then I know it's going to be up in here in quadrant 2. So it's going to look like that. So if I draw my unit circle, and I'll try to get it so it hits there, that's not bad. I know that this is my y value, so this side here, I'm going to make this a little bit bigger so you can see it better. Okay, so I've already figured out that this is going to be going here. My y value was √3 over 2. My x value is -1/2. I want to find out what this angle is. So in order to find out what that angle is, I have to take a look at my special triangles and figure out, okay, which one had the √3 over 2 as the opposite side? Well, that's the 60-degree one. Okay, so we look at the 30, 60, 90 triangle. And we find that theta would equal 60 degrees. Or if it's in radians, and because this is in radians, then I should be thinking of this in radians. It's pi over 3. But I know that the angle that I'm looking at isn't just this part. I would have had to start here and go to here. So this is actually my theta. This is my reference angle. So if I want to find out what my angle really was, I'm going to have to take and do a little bit of the math to find out what that was. So if my reference angle was equal to 60 degrees, so 60 degrees is the difference between my terminal arm, which is this line here, my hypotenuse, and this side. So that means I would take my 180 degrees, I'd subtract my reference angle of 60 degrees to get 120. Or if I was doing this in radians, so remember this would be the equivalent of a full pi. So this would be the same as saying pi minus pi over 3. So that's like 3 pi over 3 minus pi over 3, which would be, excuse me, 2 pi over 3. And 2 pi over 3 is between 0 and 2 pi, so I know my answer is okay. Okay, so what if my coordinates are √2 over 2 and -√2 over 2? So this is my x coordinate. This is my y coordinate. I draw my unit circle. X is positive, so I know it's going to be on somewhere on this axis here. My y is negative, which means it's going to be going down this way. So my square root 2 over 2 would be here. My negative square root 2 over 2 would be there. So I know it's in quadrant 4. So I draw in my angle and my right angle. So now I'm trying to, this is the angle I'm looking at. I need to find out what would be the measurement of that angle. I know this is my hypotenuse here, so that's automatically going to be a value of 1. Because I'm working just with square root 2's. Oh, sorry, I wrote that on the wrong side. This should be here. Negative square root 2 over 2 should be over there, not on that side. Because it's my y value. So I know I'm looking at a 45, 45, 90 triangle. So that means that my reference angle here is going to be 45 degrees. 45 degrees, if you remember, is the same as pi over 4. It's 1/4 of that 180 degrees. Or 1/4 of pi. Okay, so this is taking place in the 4th quadrant. So that means that I'm trying to go figure out what is this angle here. So to find that, I would be taking my 2 pi, because my closest terminal arm would be, or closest x-axis would be here, which would be back at 2 pi. So I'm going to subtract pi over 4 from that. So this is the same as saying 8 pi over 4 minus pi over 4, which is 7 pi over 4. So that would be my answer. Okay. So the last page there is just a little review of what we've done here. So it says an angle can be measured using different degrees and radians. An angle can be measured in one unit and then can be converted to the other using the relationship of a full rotation, so that 360, which is equal to 2 pi. So that's what we use when we're doing our calculations for changing from pi's, or from radians to degrees, degrees to radian. An angle in standard form has its vertex at the origin and its initial arm is along the positive x-axis. So that's just a review from last day, or last section. Angles that are coterminal have the same initial arm and the same terminal arm, so that's when we're talking about the rotations. Doesn't matter how many times it goes around, they're coterminal if they stop at the same spot. We have an infinite number of angles that are coterminal, expressed by theta is equal to plus or minus 360 degrees times n, or 2 pi times n. And then we did the arc length formula last time. I have a feeling that this is the wrong section review. I think this is from 4.1. But anyway, arc length is just theta times r. So your assignment there is on page 186, questions 1 to 8, and then 9, 13, and 15.